In today's video, we're going to analyze and write two-column proofs concerning angle and segment relationships. We're going to look at some additional postulates and theorems as we move through this lesson. The first one is the Ruler Postulate, and all this really is assigning numbers to a number line. So the coordinate for A is at 0. The coordinate for B is at 3. So we could place another point on this segment, and it could have a coordinate value of 2. So it's really just assigning points to a coordinate value on the number line. Then we have the segment addition postulate. Remember between this when we have the two parts that make up the whole. So we have the piece here that's AB, the piece here that's BC, and adding those together gives us the entire segment AC. So we're going to prove that if AB is congruent to CD, then AC is congruent to BD. So we're given this statement, so we always start with our given information. So AB is congruent to CD, and sometimes it really helps to mark those things on our pictures. Remember, we mark congruence for segments with those little dashes. Then next, from that information, we know the measurement of those are congruent. Notice how those two statements are different. The first one says that the segments are congruent. The next statement says that the measures of those segments are equal. And that follows from the definition of congruent segments. Because we know BC is equal to BC, that segment in the middle is congruent to itself. We know that AB plus BC, we're adding the same amount to BC on either side. So we have AB plus BC equals AC. And then we can replace what we know CD is equal to AB, so we can substitute that in for AB. And then again, because of our segment addition postulate, CD plus BC equals BD. Notice here, we can use the transitive property to say that AC is equal to BD, and because we're saying that those measures are equal, we then know that they are congruent. Right, this one is one for you guys to try on your own. We want to fill in the correct reason to this proof. So go ahead and pause here and look through this proof. And you should have gotten that the segment addition postulate is the missing reason. Here we want to state a conclusion that can be drawn from the statements given using the property indicated. So it tells us what our conclusion is, and using that property, what would we be able to have our next step be? So because we know LM is congruent to NO, and NO is congruent to PQ, notice NO is in both of those. So using our transitive property, we get rid of that middleman, and we see that LM is congruent to PQ. Okay, in this proof we're going to fill in some pieces. So we're given that C is the midpoint of AE, and C is the midpoint of BD, and that AE is congruent to BD. We always start out with our given information. We know that AC equals CE and BC equals CD, our definition of midpoint. So because we know that those are the midpoint, we know those pieces are equal. We also know, because the segments are congruent, that those measures are equal, that the measure of AE is equal to the measure of BD. So because of that, we can say that AE is equal to AC plus CE, due to our segment addition postulate, those two pieces equal the whole. We can substitute in AC plus CE equal to BC plus CD because we know that AE and BD are equal. So instead of AE, we're replacing that side with AC plus CE. Instead of BD, we're putting BC plus CD because that's what is equal to that. Now again, we're substituting in because we know CE is equal to AC from our statement up here. And we knew BC was equal to CD, so again we're substituting those values in. Now we have 2 of each of these. So we have 2 times AC equals 2 times CD, and we're just combining like terms. Now we divided, so we have AC equal to CD when we divide by 2. And then because we know their measures are equal, we know the segments are congruent. Our next postulate is the Protractor Postulate. It's really similar to the Ruler Postulate, except for this time we're dealing with angles. So we can assign an angle measure based on where the sides of that angle are on the protractor. So from angle A, B, C, we could assign it a protractor measure of 146. Or angle C, B, and then we could label this point D over here. And we could assign it an angle measure of 34. And the angle addition postulate is again very similar to the segment addition postulate. We have the 2 pieces, angle A, B, D, this red piece, plus C, B, D, or DBC, equal to the whole thing, A, B, C. So notice we labeled this angle X, this angle Y. This would be angle X plus Y. It's the part plus the part equals the whole. Here's an example. In this example, we can see we have angle 1 and angle 2, and then we have angle JKL. We can use the segment addition postulate to say that those 2 pieces equal angle JKL. So we've written that in an equation here, measure of angle 1 plus the measure of angle 2 equals the measure of angle JKL. And then because we know the measure of angle 2 and the measure of angle JKL, we can substitute those in. And that's really what happened here, is we substituted those values. Then subtract 56 from both sides, and we get 89 degrees for the measure of angle 1. So we can actually use our proof properties to solve problems with angle measures. Okay, next here's one for you to try. We have the measure of angle 1 is 23. Notice the measure of angle 2 is a right angle. And we want to find the measure of angle 3 because angle ABC is 131. Next we have the Supplement Theorem and Complement Theorem. Again, these follow from our supplementary and complementary properties. Angle 1 and angle 2 here are going to add to equal 180 because that's the definition of supplementary. And angle 1 and angle 2 in this problem will add to 90 because that's the definition of complementary. All right, we have an example here looking at 2 complementary angles. So we have a situation here where we drew a picture. Using a transit, a surveyor sights the top of a hill and records the angle measure of 73 degrees. What is the measure of the angle the top of the hill makes with the horizon? So we're looking for angle 2 here. So we know the measure of angle 1 plus the measure of angle 2 is 90 because of the complement theorem. But he measured angle 1 to be 73, so we can substitute that in. So we have 73 plus the measure of angle 2 equals 90. Then we can subtract 73 from both sides and get that the measure of angle 2 is 17. Okay, and then we can check our work and make sure that 17 plus 73 is 90. And that sketch really helped us here. Drawing pictures is a great way to reinforce what you're trying to show. Okay, here's an example for you to try. Next are the congruent supplements theorem and congruent complements theorem. This is saying if 1 and 2 are supplementary and 2 and 3 are supplementary, then 1 and 3 have to be equal because they add to 180 with the same angle. And so they have to be congruent to one another. It's the same with the complement. We have 4 plus 5 is 90, but 5 plus 6 is 90, so 4 and 6 have to be equal. Okay, so here's an example of the congruent supplements theorem. So it tells us that angle 1 and angle 2 are supplementary and 2 and 3 are supplementary. That's our given information. So we write that in equation form based on the definition of supplementary angles. The measure of angle 1 plus the measure of angle 2 equals 180, and angle 2 plus angle 3 equals 180. Because they both equal 180 here, we can say they're equal to each other. So I can substitute in, instead of 180, the measure of angle 2 plus the measure of angle 3. Because we know the measure of angle 2 is the same, it's equal to itself, we can subtract that from both sides of our equation and then just be left with angle 1 and angle 3. Because we know their measures are equal, we then know that they're congruent. So this is actually a proof of the congruent supplements theorem. Okay? So in this figure here, angle 1 and 4 form a linear pair, and 3 and 1 are supplementary. Prove that angles 3 and 4 are congruent. So here's what we know. Here's what we're trying to show. We're starting with our given information. Measure of angle 3 plus the measure of angle 1 equals 180, and 1 and 4 form a linear pair. Okay, so we know 1 and 4 are supplementary because of the definition of a linear pair. 1 and 3 are supplementary because it tells us their measures add up to 180. And we know the measure of angle 3 is equal to the measure of angle 4. So they are congruent because of that supplement theorem, that angles supplementary to the same angle are congruent. So instead of writing out what that reason is, you could have just put the supplement theorem. Okay, here are some more theorems that we have. The vertical angles theorem. Remember, vertical angles are congruent. So angle 1 and angle 3 are vertical angles here. And angles 2 and 4. Then we also have some right angle theorems. Perpendicular lines intersect to form 4 right angles. So we have this example here. If AC is perpendicular to BD, then we know that angle 1, 2, 3, and 4 are all 90 degrees. All right angles are congruent. Well, if all right angles are 90 degrees, then all of them have to be congruent. So in this picture here, we know angle 1 congruent to angle 2, congruent to angle 3, congruent to angle 4. The next theorem for right angles, if we know that these are perpendicular lines, then we know that angle 1 and angle 2 are both 90 degrees. So congruent adjacent angles is that next theorem. Because they're next to each other and they're both right angles, we know they have to be congruent. So those linear pairs, when we have perpendicular lines, are going to be congruent. If two angles are congruent and supplementary, then each angle is a right angle. So if they're congruent, but they're also supplementary, the only way for that to happen is if they're both 90 degrees. So to be congruent means to have equal measure, and supplementary means they have to add to 180. So you'd have both of them that are the same, so divide 180 by 2, and they both have to be 90. And if two congruent angles form a linear pair, then they are right angles. So if we know that 7 and 8 form a linear pair, and they're congruent, then we know they have to be right angles. All right, our last example, we have a proof where DB bisects ADC. That means that angle 1 and angle 2 have to be congruent because of the definition of an angle bisector. 1 and 3 are vertical angles, so we know that angle 1 and angle 3 are congruent. And then angle 3 is congruent to angle 2 because of the transitive property, 1 congruent to 2, and both of those are congruent to 1, so they're congruent to each other. And then the symmetric property, angle 2 is congruent to angle 3.